Hi, welcome to my channel, Math Made Easy with Laurel. I'm Laurel, and in this video we're going to take a look at the definite integral. In the previous few videos, we defined and found indefinite integrals, and we're going to be doing much of the same thing in this video, except we're going to go one step further. We're going to evaluate those integrals at certain values. So first of all, let's define what a definite integral is. The integral, and you'll notice a letter at the bottom, a letter at the top, those will typically be numbers called the lower limit and the upper limit of small f of x dx will be equal to capital F of b minus capital F of a, where the derivative of capital F of x is equal to small f of x. So you're still going to be finding the integral of this function the way we did in the last couple of videos, but you're going to take it one step further. You're going to calculate capital F of x when x is b. You're going to calculate capital F of x when x is a, and you're going to subtract. Because you're subtracting those two integrals and each one has the same constant attached, when you subtract the one constant from the other, it disappears. So we don't worry about constants when we're doing definite integrals. This is called the Fundamental Theorem of Calculus, and I want to just show how this works with an example. When you look at the examples of definite integrals, they will look something like that. You're going to have numbers in your lower and upper limits, and you're going to have your f of x dx. So you're going to integrate first. So the integral of x squared will be x to the add a 1, so x cubed. Divide this 1 by my new exponent, so that will be 1/3. And then instead of putting plus c, we're going to indicate that we're going to evaluate it at 5 and at 1. And the way that we do that, it was with a straight line, following the function, and we put the 1 and the 5 in the lower and upper positions. Now we're going to evaluate at b, or at the top number, so it will be 1/3 5 cubed minus, then we evaluate at the bottom number, 1/3 1 cubed. So we're going to get 125 thirds minus 1/3, which is 124/3. I prefer exact values. I'd rather not change this to a decimal. So let's just leave it as 124/3. That's how you evaluate definite integrals. You first of all integrate the way we were doing, but we don't bother with the constant of integration. We indicate that we're going to evaluate it at these two values. We plug the top number into the function first, subtract, plug the bottom number into the function, and then evaluate. Let's take a look at some more examples. In our first example, we're finding the integral of 2x cubed. So we add 1 to our exponent, so it'll be x to the 4th. We take 2, we divide by our new exponent, so 2/4 will be 1/2. And then I indicate that I am going to be evaluating it at these two numbers with that line. And then I simply plug my top number in, so 1/2 3 to the 4th minus 1/2, put my bottom number in, 1 to the 4th. And when I evaluate it, I'm going to get 81/2 minus 1/2, which is 80/2, which is 40. And you're done. You might have a polynomial. So we integrate each term the way we have done previously. So this will be x to the 4th, 1 divided by 4, minus, this will be x cubed, 3 divided by 3 is 1, plus x squared, 6 divided by 2 is 3, minus 8x. Put brackets before you put your line. We're evaluating at 2, and we're evaluating at 0, and we're going to subtract. The other option is you could use square brackets and then put your two numbers at the top and the bottom of your square bracket. Now we evaluate it. So 2 to the 4th is 16 divided by 4 is 4, minus 2 cubed is 8, plus 2 squared is 4 times 3 is 12, minus 16, minus, when we put a 0, every term is going to be 0. So we're going to have negative 8 as our answer. Let's take a look at this example. Before we can integrate, we have to rethink or rewrite this function because we don't know how to integrate it when it's in this form. So we're going to write that as x to the negative 1/2. When it's in the denominator, it's x to the 1/2. And then when we bring it out of the denominator, it becomes negative. So to integrate, I add a 1 to my exponent. Negative 1/2 plus 1 is positive 1/2. I take my original coefficient of 1, divide by 1/2. 1 divided by 1/2 will be 2. So that's the integral. And now I'm going to evaluate it. So it will be 2 times 4 to the 1/2 minus 2 times 1 to the 1/2. Square root of 4 is 2. 2 times 2 is 4. Minus 1 to the 1/2 is 1 times 2 is 2. So my answer will be 2. Let's take a look at some more examples. Our next example is a function raised to a power. So we're going to take a look at our power rule. To use the power rule, if you have a function raised to a power, you need to have your du factor and it needs to be exact before you can integrate. So if we look at this as u to the n, we want to know if we have our du factor. So we can define u, which is x squared plus 1. The derivative of that is 2x, so the differential of that will be 2x dx. Do I have that du factor? I have the most important part of it. I have the x. I don't have the 2, but that's not an issue. I can introduce a 2 as long as I balance it by introducing a 1/2. So if I can multiply by 2 as long as I also multiply by 1/2. And when I multiply by 1/2, I'm going to do that outside the integral sign. Now that I have my du factor and it's exactly what it needs to be, I basically ignore it. I plug into this formula and the du doesn't appear in the result. So when I integrate this according to my power rule, I have 1/2 u, which is x squared plus 1 to the power of n plus 1 to the power of 4, divided by n plus 1. And instead of plus c, it's a definite integral, so I indicate that with this line. I'm going to simplify it first, so it would be 1/8 times x squared plus 1 to the 4th power. Now I evaluate it. I can either leave the 1/8 factored out of both terms or I can include it when I'm evaluating it. It's personal choice. I'll just leave it in there. 1/8, I've got 1 squared plus 1, which would be 2 to the 4th. Then I plug in a 0. 1/8 times 0 plus 1 is 1 to the 4th. 2 to the 4th is 16. 16 divided by 8 is 2 minus 1/8. That's 16/8 minus 1/8 would be 15/8. That would be the definite integral. In the next question, we have another power. So this is our u to the n. Therefore, we're defining u as 4x minus 1. The derivative will be 4, so the du factor will be 4 dx. I don't have the 4. I have a 5, but that's not going to be part of it. So what you can do is move that 5 in front of the integral sign. It has nothing to do with the du factor. And then we're going to introduce a 4. We're going to multiply by 4 so that I have my du factor exact. But if I multiply by 4, I also have to divide by 4, and I can do that outside the integral sign. Now I have u to the n, and I have du. I didn't here, so we couldn't integrate it yet. So remember, it's important that you get that exact before you can integrate it. Now we're going to integrate, so it's going to be 5/4 u, which is 4x minus 1 to the power of 2 plus 1 is 3 over 3. And that will be equal to, when I simplify it, 5 over 12. And now I evaluate it. This time when I evaluate it, I'm going to leave the 5/12 right out. That might be a little bit easier. And then I plug 2 in for x. So 4 times 2 minus 1 is 7. So 7 cubed. Minus, we plug a 1 in. 4 times 1 is 4, minus 1 is 3. So 343 minus 27. So when I subtract 27 from 343, I get 316. And then what I did is I reduced this whole thing to 395 over 3. In our next example, we have two separate terms. Normally, we've seen that when we've had polynomial functions, and you just integrate each term without actually splitting them up formally. So this is an example where I do need to split up my two terms. When I split them up, it will look like this. I'm going to take the integral of 4x dx plus, I'm going to write this as 3x plus 1 to the 1/2 dx. I need to integrate these separately because I'm going to be introducing a du factor for this term that shouldn't be included in this term. In order to integrate this, it's just simply going to be x squared. 4 divided by 2 would be 2x squared. I'll put my line behind it. Plus, when I integrate this, I'm going to be using my power rule. So I've got u to the n. My du factor will be 3 dx. The derivative of 3x plus 1 is 3. I don't have the 3, so I'm going to introduce it as long as I balance that. Now that I have my du factor and it's exact, I can plug into my formula. So this will be 1/3 u, which is 3x plus 1 to the n plus 1, so 3/2, divided by 3/2. And again, I'm going to indicate that it's a definite integral with that line. Because both of these are going to be evaluated at 1 and at 0, I can combine them and say that it's going to be 2x squared plus, when I simplify this, 1/3 divided by 3/2 will be 1/3 times 2/3, which would be 2/9. 3x plus 1 to the 3/2. And then I can just put my notation when I'm using my square bracket for my lower limit and my upper limit like that. Now let's evaluate. So I put a 1 in this whole expression. So it will be 2 times 1 squared. It would be 2 plus 2/9 times 1 times 3 is 3 plus 1 is 4. The square root of 4 is 2. 2 cubed is 8. Minus, now I evaluate this when x is 0. This term will be 0. When I put a 0 in here, that'll be 1. 1 to the 3/2 is 1, so it will be 2/9. 2 plus 16/9 minus 2/9 will be 2 plus 14 over 9. Get a common denominator, so we're going to have 18 over 9 plus 14 over 9, which would equal 32 over 9. You're going to notice that fractions come up a lot when you're doing definite integrals. Again, you could change it to a decimal if you prefer. I prefer exact values, so I typically will leave them as fractions. So practice doing definite integrals as much as you can. Get very competent in evaluating them, because we're going to be using them in a number of applications. In the next video, we're going to be talking about area under curve, in which we use definite integrals. And then there are many other applications that we'll take a look at shortly. So take care, and we'll see you on the next video.